collective resource you have. We'll start with what makes a tree, move through its fundamental properties, analyze distances, and then finish up with some really elegant ways to count them, including the legendary Prüfer code.
All right, let's jump right in.
Let's do it.
Okay, so let's unpack this right at the foundation. When we look at this, this tangle of vertices and edges that we call a general graph, what is the single non-negotiable feature that elevates it to the status of a tree?
The defining feature is acyclicity,
Acyclicity.
a graph that contains no cycles. I mean, think of a cycle as just a closed loop, a way to start at point A, travel along some edges, and then get right back to A without, retracing your steps.
Because you can't get back to where you started without turning around.
Exactly. If you eliminate all of those loops from a graph, what you have left is an acyclic graph.
So we're starting with this broader category of loop-free structures.
Precisely. And we call that a forest. Definition 1.1 states that a forest is an acyclic graph. Now, the crucial part here is that a forest can be disconnected.
Oh, okay.
Imagine a few small islands, and on each island, the roads and paths form no closed loops. All those islands together as a group, they constitute a forest.
So a collection of trees, basically.
A collection of trees, yes. And that brings us to the distinction, the difference between that scattered forest and a single tree.
It has to be connection.
It's connection. Definition 1.2 tells us a tree is a connected acyclic graph. That pairing connected and no cycles, that's the minimal requirement for holding them vertices together without any redundancy. If you satisfy both of those, you're guaranteed to have a tree.
In that lack of redundancy, that structural requirement, it immediately imposes some really fascinating and highly predictable rules on how these graphs have to behave, especially at their endpoints, the leaves.
The leaves, right. These are the vertices with a degree of exactly 1. They are the terminal nodes of the structure. And Theorem 17.1 gives us this beautiful, simple rule about them. Every tree with at least 2 vertices has to have at least 2 leaves.
You can't have a non-trivial tree that just, closes in on itself or has only one end?
You can't. It's impossible. And while that seems intuitive, the mathematical proof for it is really elegant.
Okay, walk me through it. How do we prove that you can't build a connected, cycle-free thing with only 1 leaf or 0 leaves?
The proof sketch uses a simple thought experiment. It's called the longest path argument. So, since the graph is connected and it's finite, there has to be a path of maximum possible length, right?
Sure, there's a longest road somewhere in the network.
Exactly. Let's call this path P and say it runs from vertex V1 to vertex Vk. The argument is that the endpoints, V1 and Vk, they must be leaves. They have no other choice.
Why must they be? What goes wrong if they aren't?
Well, suppose V1 was not a leaf. That means it must be connected to some other neighbor, let's call it that isn't V2, its neighbor on the path.
Okay.
Now, there are 2 possibilities for this neighbor. If U is already on our path P, then we have a problem.
A big problem.
A very big problem. Then V1 and U are connected in 2 ways. The new edge from V1 to O and the segment of the path P that already connects them. That immediately creates a cycle.
And that violates the definition of a tree, so you can't be on the path.
Right. So what's the other option? U is not on the path P. But if that's the case, then we can create a new path starting at U, going through V1 and then all the way to Vk. This new path is 1 edge longer than P.
Which contradicts our starting point, that P was the longest path.
Exactly. We hit a contradiction in every single scenario where an endpoint isn't a leaf. So the endpoints must be leaves. And since a path has 2 endpoints, this guarantees at least 2 of them.
That makes the structure feel very rigid and predictable. Okay, so what happens when we modify a tree? Does it keep its properties?
If you modify it carefully, yes. Theorem 17.2 looks at deletion. If you take any n-vertex tree and you delete a leaf, you are always left with another tree, just with n-1 vertices now.
Wait, so if deleting any leaf preserves the tree property, does that mean no single leaf is truly critical to the structure?
That's precisely the point. Removing a leaf V and its 1 edge doesn't create any new cycles because the graph was already cycle-free. But more importantly, it can't disconnect the remaining graph.
Right, because the leaf was only connected to 1 neighbor.
Only 1 neighbor, U. So removing it can't possibly sever U's connection to the rest of the structure. The resulting grad is still connected and still cyclic. It's still a tree. This property is absolutely crucial for recursive algorithms that operate on trees.
That's deletion. So let's look at the opposite addition. What happens if we add a new edge, say edge E, between two vertices u and v that were already part of the tree.
This is covered in Theorem 3.2 and 17.3, and it's a foundational result on tree behavior. Adding one single edge to a tree always creates exactly one cycle.
Not 0, not 2. Exactly 1.
Exactly one. And the reason for this is rooted entirely in a property we're about to see is fundamental to trees, the unique path property.
Okay, so in a tree, there's only one way to get from any point A to any point B.
One and only one path. So if you then introduce a new edgy between those 2 points, U and V, you're basically creating a second alternative route. The original unique path, combined with this new edgy, forms a single closed loop, a cycle. And since no other paths existed, you're mathematically forbidden from creating any additional cycles. It's a minimal addition that results in a minimal loop.
This feels like it's leading somewhere really important.
It is. This next section is arguably the most important one for your study notes, the fundamental theorem of trees. It takes that basic definition we just covered and expands it into 4 mathematically equivalent statements.
So 4 different ways of looking at the same object.
Exactly. And this gives you immense power because it lets you prove a graph is a tree using structural criteria, numerical criteria, or connectivity criteria, depending on what's easiest in your context.
All right, let's
You
list
can
them out
do
carefully
it.
so we can all get
Let's
them
work
down.
today
We'll
to
start
make
with the one we
tomorrow a
already
better
know.
day.
Number 1.
Okay.
G is
You can
connected
do
and
it.
acyclic.
Let's
This
work
is our
today to
standard
make
dual
tomorrow
property
a better
definition.
day.
Okay.
Number 2.
Okay.
G is
You
connected
can
and
do
has
it.
n-1
Let's
edges.
work.
This is a property based on, well, numerical efficiency.
Number 3.
G has n-1 edges and no cycles. So it's a property based on that same numerical parsimony but paired with the structural rule.
And the last one feels like it ties back to what you just said about paths.
It does. Number 4. For every pair of vertices U and V, there exists exactly one UV path in G, a property based purely on connectivity guarantees.
What's so powerful about these is how restrictive statements 2 and 3 are. They tell us a tree is the most efficient possible connected structure.
It is. You have precisely enough edges to make sure everyone is linked, but not a single extra edge that could create redundancy or a cycle. n-1 is the magic number.
If you had n-2 edges, you'd be disconnected.
Guaranteed. And if you had n edges, you'd either have to be disconnected or, much more likely, you'd contain a cycle. This theorem shows these properties are just completely inseparable.
Let's trace the logic connecting them. Understanding the proof sketches is really the key to deep understanding. So how do we show that number 1, the standard definition, implies number 2, the numerical constraint?
We use that sequential leaf removal trick we just talked about. If G is a tree, we know it's connected and acyclic.
Right.
Theorem 17.2 guarantees we can find a leaf, delete it and its single edge, and be left with a smaller tree. We can just keep doing this one leaf at a time.
You peel it like an onion.
Exactly. You repeat this n-1 times. You start with n vertices, you end with one single vertex left. And since you removed exactly one edge in each of those n-1 steps, the original graph must have had n-1 edges. So being connected and acyclic forces the edge count to be n-1.
Okay, so 1 implies 2. That shows the efficiency is built into the structure. Now, how does being connected with n-1 edges, number 2, guarantee no cycles? Which gets us to number 3.
This is a proof by contradiction, and it relies on the minimum edge requirement for connectivity. We already know that any connected graph on n vertices must have at least n-1 edges.
That's the bare minimum.
The bare minimum. So let's suppose our graph G is connected and has n-1 edges, but contrary to what we want to prove, it does contain a cycle.
Okay, so we're assuming it has a loop.
We're assuming it has a loop.
Right.
Well, if a cycle exists, we can remove any one edge from that cycle and the graph will stay connected. There's always an alternate route through the rest of the loop.
And if we remove an edge but stay connected, we now have a connected graph with only n-2 edges.
Precisely. And that contradicts the proven fact that you need at least n-1 edges to connect n vertices. Therefore, our initial assumption that a connected graph with n-1 edges could have a cycle must be false. So 2 implies 3.
That is incredibly elegant. It's like the graph is so taut, so efficient, there's no slack for a cycle to form.
That's a great way to put it.
So that economy of edges, what does it impose on the paths themselves? Moving from 3, having n-1 edges and no cycles, why does that imply the uniqueness of paths, number 4?
If a graph has n-1 edges and is acyclic, it has to be connected. We just showed that. The critical link now is the acyclicity. If there were 2 different paths between some vertices U and V, let's say P1 and P2.
Okay, they would have to form a loop.
They would necessarily meet and diverge somewhere, forming a closed loop, a cycle. Since we are guaranteed by our premise to have no cycles, the path between any two connected points must be unique. So 3 implies 4.
And finally, we have to close the loop. Unique paths, number 4, has to circle back and prove the original definition of a tree, number 1.
Yes, and this is probably the most straightforward link. 4 implies 1. If there's at least one path between every pair of vertices, well, by definition, the graph is connected. And if there is exactly one path, the graph must be acyclic, because as we just said, having 2 paths would create a cycle, and that violates the uniqueness constraint. So the guarantee of a single unique path confirms both connectivity and acyclicity, and that's the definition of a tree.
That closed loop of logical certainty is why this theorem is so foundational. It gives us 4 robust, interchangeable tools for defining and verifying a tree, which has to be vital when you're designing systems that demand minimal redundancy.
Absolutely. We've established the core identity of a tree. Now we can start to examine the specific roles played by its components and, how a tree relates to larger, more complex systems.
Let's start with the role of the edge itself. Theorem 3.1 or 17.5 seems to give every single edge in a tree a really critical structural role.
It does. Every edge in a tree is a cut edge. It's also commonly called a bridge. What this means is that if you remove any single edge, you immediately disconnect the graph.
The whole thing falls apart.
It splits into 2 pieces. And this is a direct consequence of that unique path property we just established as an equivalent definition of a tree.
Help us visualize that with a real-world network analogy.
Okay, imagine a basic computer network laid out as a tree, no redundant wiring, just the bare necessary links. If the connection between node A and node B is the edge E, that edge represents the only way for A and B to communicate.
There's no backup road.
No backup. So if you cut that wire, the path is gone. The network splits. The tree is what we call minimally connected, which means it has 0 tolerance for failure in any single edge.
That really highlights the essential tension of a tree, doesn't it? It's highly efficient, but not very robust.
Precisely. Now, let's move to a related concept, the spanning tree. A tree doesn't have to exist in isolation. It can be the structural skeleton of a much larger, denser, and, potentially redundant network G.
And definition 3.3 or 17.7 confirms that these skeletons always exist. It says every connected graph G contains at least one spanning tree.
Think of the full graph G as a complex metropolitan subway map with lots of redundant lines and loops. A spanning tree is the minimal version of that map. It's the set of tracks that ensures you can still get to every single station, but without any loops at all.
And the proof for its existence actually tells us how to find one, how to extract that minimal structure.
It's a constructive proof, which is really nice. If your full subway map G has cycles, you just find an edge that's part of a cycle and delete it.
And the graph stays connected because there was an alternate route through the rest of the loop.
Exactly. Connectivity is preserved. You just repeat this process, iteratively deleting edges that belong to cycles until no cycles remain. What you have left is a connected, a cyclic subgraph that contains all the original vertices. And that is a spanning tree. This process is the foundation of many network optimization algorithms.
So once we find one spanning tree in a graph, how similar are all the other possible spanning trees you could find in that same graph?
They are very intimately related thanks to a beautiful idea called the exchange property. This is from Proposition 4.1 or Theorem 17.4. And this property shows that all spanning trees are reachable from one another through a series of single-edge swaps.
Okay, explain the mechanism of the swap. How does that work?
So you have 2 different spanning trees of the same graph. Let's call them T and T prime. Now, you take an edge, E, that is in T, but it's not in T prime.
Right.
If you add that edge E to T prime, what happens? We just learned this. It has to create exactly one cycle.
Exactly one cycle.
Now, you look at that new cycle, you can choose any edge, let's call it E prime, from that cycle that belongs to T prime, but not to T. And if you swap them, you remove E prime from T prime and add an E, the result is another valid spanning tree.
So you can morph any spanning tree into any other one edge at a time.
One swap at a time. This guarantees you can move from any minimal skeleton of the network to any other minimal skeleton by just adjusting one link. This relationship is crucial for optimization problems, like finding the minimum spanning tree.
That's a beautiful symmetry. Before we get to measuring distances, there's one last powerful structural rule here.
Yeah.
The tree embedding criterion. This tells us when a smaller tree is guaranteed to fit inside a larger, denser graph.
Yes, Proposition 5.1. This is a very robust result for, say, network robustness. If you have a tree T with K edges, and you have a simple graph G, where the minimum degree delta of G is greater than or equal to K.
So every single node in G is connected to at least K other nodes.
Right. If that condition holds, then the tree T is always a subgraph of G. You are guaranteed to find it inside.
What does that tell us about network design?
It tells you that if the minimum local connectivity in your large network is high enough, you're guaranteed to have enough redundancy to contain that specific K-edge tree structure. It gives you a formal, predictable bound on when containment is guaranteed based purely on local density.
Okay, we've established the structure. Now we need to quantify how connections are actually measured within these graphs. Since graphs model things like communication and travel, distance is obviously the next crucial metric.
Right, we move from topological properties to measurable metrics. The first one, definition 6.1, distance, dg of u, v, is very straightforward. It's just the length of the shortest path between u and v.
In a physical network, this would be the minimum number of hops a packet has to take to get from one node to another.
Exactly.
Right.
And building on that, we get a measure of how far away a single vertex is from the absolute furthest point in the graph. That's its eccentricity.
Eccentricity, E of V.
It's defined as the maximum distance from your vertex v to any other vertex in the graph. So E of v is the max over all u of the distance from u to v. Think of it as the worst-case journey time, starting from v. If you're a communication hub, your eccentricity tells you the longest you might have to wait for a response from the most remote node in your network.
And these individual eccentricities then define the two critical global measures for the entire graph, radius and diameter. These two get confused all the time, so we need crystal clarity here.
Yes, the distinction is vital. The diameter of a graph, diam of g, is the maximum eccentricity across all vertices.
Biggest of the worst-case journeys.
The biggest of the worst cases. It's the longest, shortest path in the entire graph. If you want to know the absolute maximum necessary travel time between any 2 points in your network, you look at the diameter.
And the radius.
The radius, rad of g, is the minimum eccentricity. It represents the shortest possible worst-case journey time. The vertices that achieve this minimum eccentricity, they are the best connected vertices in the whole graph.
They are the closest a node can be to its furthest point.
Exactly. And they define what we call the center of the graph.
This is where we find a really surprising result, the complementary bound from theorem 6.1, or 17 point yin. This links a graph G to its complement, G bar, which is the graph of all the edges that are missing from G.
It's a really elegant demonstration of duality. The theorem states that if the diameter of G is relatively large, say greater than or equal to 3, then the diameter of its complement, G bar, must be relatively small. It has to be less than or equal to 3.
You can't have a situation where both the original network and the network of its missing connections are widely spread out.
You can't have both be distant. Let's walk through the intuition. If the diameter of G is at least 3, that means there's at least one pair of vertices, u and v, that are 3 or more steps apart.
So they aren't adjacent, and they don't even have a neighbor in common.
Exactly. Now let's look at the complement, G bar. Since u and v are non-adjacent in G, they must be adjacent in G bar. So the distance between them in the complement is 1.
Ah, okay.
And you can extend this logic to any 2 arbitrary vertices. The whole argument forces the diameter of the complement to be small. The message is, a graph is either tightly connected itself or its gaps, the complement, are tightly connected. One or the other has to be true.
Shifting back to trees, where are the absolute best locations for optimal connectivity? That brings us to the center.
The center is defined as the subgraph made up of all the vertices with the minimum eccentricity, the nodes that are closest to everyone else in the structure.
For a general graph, the center could be some complex cluster of nodes. But for a tree, theorem 6.2 or 17.11 gives us one of the most remarkable and simple results in all of graph theory.
It's beautiful. The center of any tree is restricted to be either a single vertex or a single edge, meaning 2 adjacent vertices. It cannot be any larger or messier.
Why this guaranteed simplicity? What forces it to be so small?
We go back to that iterative leaf removal process. When we defined the leaf property, we talked about pruning. Well, if you continually remove all the leaves from a tree simultaneously, in each step, the structure that's left is still a tree.
And crucially,
the eccentricities of the remaining vertices decrease uniformly by 1. You're basically peeling back the structure symmetrically from all sides at once. This process has to eventually shrink the tree down until only its innermost core is left.
and because the reduction is symmetrical.
The core can't be a complex cluster. It has to be either a single, centrally located vertex or two vertices connected by the final remaining edge.
Amazing. Okay, so we've moved from structure to measuring the longest paths.
Okay.
Now let's look at the collective effort for travel across the whole graph, the total distance cost.
This collective measure is called the Wiener index. Definition 7.1 states that the Wiener index, W of G, is the sum of all the shortest path distances between every distinct pair of vertices in the graph.
So it's a single number that quantifies the overall internal connectivity and efficiency of the entire network.
It is. If you were modeling logistics, W of G would represent the total energy cost or time delay for all possible communication pairs across the network. A lower Wiener index means a more efficient graph.
And Theorem 7.1, or 17.1, uses this to find the two most extreme trees on n vertices. Let's start with the most efficient one. Which tree structure minimizes the Wiener index?
The minimum total distance is achieved uniquely by the star graph, K1, n minus 1.
This is the structure with one central hub connected directly to all the other nodes, which are all leaves.
Right. And it's so efficient because travel is optimized around that center. Any journey that doesn't involve the center, say from one leaf to another, takes exactly 2 hops. Leaf to center to leaf.
And any journey to or from the center is just one hop.
Exactly. Since the vast majority of pairs are only distance 2 apart, the total sum of distances is as low as it can possibly be. It's the model of extreme centralization.
So what's the
You
opposite?
can do
The
it.
structure that
Let's work
maximizes the
today
Wiener
to make
index.
tomorrow a better
The
day.
most spread out,
Okay.
inefficient tree.
You can
That
do
is
it.
uniquely the path
Let's
graph,
work today to
Piana.
make
Just a
tomorrow
straight
a
line of
better
vertices
day.
arranged
Okay.
sequentially.
Like an inefficient
can
supply
do
chain
it.
where
Let's
every
wo-
connection has to go through a long sequence of handoffs.
The path maximizes the shortest distances, especially between the endpoints, which are n-1 steps apart. This pulls the total Wiener index as high as possible, and the proof idea really supports this contrast. Any balancing move that takes a leaf away from the end of a long path and reattaches it closer to the center always reduces the total Wiener index.
So optimization is always a move away from the path and towards the star.
It is. This establishes a clear spectrum for network efficiency in trees.
Now moving beyond trees, how does adding edges affect distance in a general graph?
That brings us to a really fundamental distance inequality for subgraphs. It's lemma 8.1 or 17.9. If you have a subgraph H that's contained within a larger graph G, then the distance in G is always less than or equal to the distance in H.
Adding edges never increases the shortest distance. It can only create shortcuts.
That's the perfect way to put it. Every path that existed in H is still available in G, but G might introduce new, shorter paths because of the extra edges. This principle is straightforward, but it's essential for understanding things like network resilience and shortest path algorithms.
In using this principle, we can place an overall upper bound on the total distance for any connected graph G, even if it's full of cycles.
Yes, Section 9 confirms this powerful bound. For any connected n-vertex graph G, its Wiener index, W of G, has to be less than or equal to the Wiener index of the path graph, W of Pn.
So you can't be more spread out than a path.
You can't. Since the path graph is the maximally inefficient tree and a tree is the minimally connected structure, the path sets the absolute ceiling for the total cost of travel in any connected graph on n vertices.
Okay, we've analyzed structure and distance. Now we arrive at a classic mathematical challenge. How many different trees can you actually make on a set of labeled vertices?
This is the problem of enumeration. And the key, as you said, is that we're talking about labeled trees where vertex 1 is different from vertex 2. And this problem was solved by creating a one-to-one correspondence, a bijection between trees and sequences using the really elegant proof-for-code algorithm.
The proof for code is brilliant. It translates the complex, 2D topology of a tree into a simple linear sequence of numbers that's easy to count.
It really is.
Okay, let's walk through the algorithm slowly and make sure it's clear for the study notes. We start with a labeled tree, T, with n vertices.
And we repeat a very mechanical process n-2 times. In each step, you do 3 things. 1, identify the smallest labeled leaf currently in the tree.
Smallest number on a node with degree 1.
Right. 2, record its neighbor. The label of that neighbor becomes the next number in your proof or sequence. And 3, delete the leaf and its edge.
And you just keep doing that until only 2 vertices are left. This gives you a sequence of numbers of length exactly n-2.
And the beauty of it is the bijection. Every unique labeled tree corresponds to exactly one of those sequences. And critically, every single possible sequence of that type can be used to reconstruct exactly one unique labeled tree.
And that leads directly to the famous counting result known as Cayley's formula.
It does. Since the proofer sequence has n-2 slots, and each of those slots can be filled by any of the n-vertex labels that can repeat, the total number of possible sequences is just n times n times n-2 times.
So n to the power of n-2.
The total number of labeled trees on n vertices is exactly n to the n-2.
That is such a definitive, powerful, and clean result, and it comes from such a simple, systematic coding process.
We can even extend this to count trees with specific characteristics. This moves us to the prescribed degree sequence from Theorem 10.1. What if we want to count only the trees where the degree of each vertex I is fixed to some number, di?
First, there's a constraint, right? The sum of all those degrees has to equal 2 times n-1.
That's right. That's the handshaking lemma for trees. Once that's met, the formula for the count is given by a multinomial coefficient, n-2 factorial, divided by the product of di minus 1 factorial for all I.
Okay, that looks a little dense, but you mentioned it ties back directly to the proofer code. So how does the degree of a vertex relate to its appearance in the code?
This is the key insight. A vertex I gets recorded in the proofer sequence every time one of its neighbors is chosen as the smallest leaf and gets deleted. This means a vertex I appears in the proofer sequence exactly di minus 1 times, where di is its degree in the final tree.
Ah, so if a vertex has degree 4, it must have been recorded 3 times in the sequence. If it's a leaf, with degree 1, it gets recorded 1 minus 1, so 0 times.
Exactly. And since we know the total length of the sequence is n-2, and we know exactly how many times each label must appear, the problem just reduces to calculating the number of unique permutations of that sequence. And that's precisely what the multinomial coefficient does.
So the formula is a direct consequence of how the proofer algorithm works. That's fantastic.
It is.
We've mastered counting trees themselves. Now let's tackle counting how many distinct spanning trees exist within a larger, denser cyclic graph G. This has to be vital for measuring things like network resilience and redundancy.
Yes, this moves us into counting substructures. And we have two main methods. One is based on a beautiful recursion, and the other is based on powerful algebra. Let's start with the recursive one, which relies on an operation called edge contraction.
Okay, define contraction for us carefully.
To contract an edge E that connects U and V, you physically merge U and V into a single new supervertex. All the other edges that used to connect to either U or V now connect to this new vertex. Then you just clean it up, remove any loops that might have formed, and if you have duplicate edges, you just keep one.
This sets the stage for the deletion contraction formula, which is one of the most beautiful recurrences in all of combinatorics.
It really is. If we say tau of G is the number of spanning trees of a graph G, the formula is tau of G equals tau of G minus E plus tau of G divided by E, which is the contraction.
It's almost poetic. It breaks this massive counting problem down into 2 simpler, mutually exclusive parts, all based on the status of one single edge, E.
Think about it like this. You're looking at all the possible spanning trees. Every single one of them must either exclude the edge E or it must include the edge E. There's no third option.
The number of trees that exclude E is just the number of spanning trees in the graph with that edge deleted, so tau of G minus E.
That's the first term. Now, if a spanning tree includes the edge B, what does that mean? It means U and V are connected by that edge. We can effectively collapse them into one point, and the remaining edges of that spanning tree still form a spanning tree on the now smaller contracted graph.
So that's the second term, tau of G contracted on E.
That's the second term. This recurrence lets you keep breaking the problem down into smaller and smaller graphs until you're left with trivial cases you can just count.
That's the recursive method. What's a powerful algebraic approach?
That would be the matrix tree theorem. This uses linear algebra to give you a direct, deterministic calculation without any recursion.
So we have to define the graph using matrices.
We do. We start with the adjacency matrix, A, which just records which pairs of vertices are connected. Then we create the diagonal degree matrix, D, which lists the degree of each vertex down the diagonal.
And you combine these two to form the crucial matrix, the Laplacian Q.
Correct. The Laplacian Q is just D minus A. It captures the essence of connectivity and flow in the graph. And the theorem states that the number of spanning trees, tau of G, is equal to the determinant of any cofactor of Q.
Meaning you delete any one row and its corresponding column from Q, and then take the determinant of what's left.
And the amazing thing is, it doesn't matter which row and column you delete. you always get the same answer.
The power here is that this single determinant calculation just gives you the final count. No iteration needed.
Exactly. The underlying mathematics is fascinating, but the short version is that when you calculate this determinant, the algebra is set up in such a way that all the non-tree subgraphs cancel each other out, and you're left with exactly the count of all the spanning trees. It's an essential tool for analyzing large networks where recursion would be computationally impossible.
Okay, we have covered the core definitions, distances, and counting mechanisms. Now let's shift our focus to some specialized forms of trees and move into the really exciting frontiers of research, the problems that are still stumping mathematicians today.
We can start with the concept of symmetry and beauty captured in graceful labeling.
This sounds elegant.
It is. Gracefulness is a very stringent labeling requirement for a graph G with M edges. The definition puts a huge structural constraint on how you're allowed to label the vertices.
What are the two conditions for this perfection?
First, the vertex labels themselves have to be distinct, and they have to come from the set of numbers from 0 to m. Second, when you calculate the labels for the edges, which you get by taking the absolute difference between the labels of their endpoints, these edge labels also have to all be distinct, and they have to perfectly equal the set from 1 to m.
Wow, that is demanding perfect numerical symmetry. You're asking for the vertex positions to generate a complete, unique set of differences that corresponds exactly to the number of edges.
It's the ultimate test of structural balance, and this leads directly to Rose's conjecture from 1966, one of the great open problems in graph theory. Every tree is graceful.
It's been proven for lots of types of trees, but not for all of them.
The general case remains elusive, and the reason the symmetry is so important is because it links to how graphs can be fitted together, like tiling a much larger, denser graph.
Right. Theorem 13.1, or 17.1 and 6 reveals this profound consequence.
It does. If a tree T with n edges is graceful, then the complete graph K2n plus 1, where every vertex is connected to every other vertex, can be perfectly decomposed into two n plus 1 edge disjoint copies of T.
So a complete graph is the most redundant network possible. And a graceful tree can perfectly tile that massive, dense space with no overlaps and no gaps. That kind of symmetry is just profound.
It is. The graceful labeling provides the necessary numerical framework that lets you rotate and shift the tree in a way that perfectly fills all the edges of that larger, complete graph.
Let's turn to some specialized tree structures, starting with caterpillars.
Caterpillars are a highly regular subclass of trees. The definition is pretty simple. They're trees where all the vertices are either located on a single central path, we call that the spine, or they're adjacent to a vertex on that spine.
So they're basically just paths with little appendages or legs sticking out, hence the name.
Exactly. And Theorem 14.1 or 17.1 gives us a clear structural characterization by telling us what they cannot contain. A tree is a caterpillar if and only if it does not contain a specific Y-tree structure as a subgraph.
Okay, describe that Y-tree structure for us clearly.
The forbidden Y-tree is a central edge that has 3 arms branching off it, and each of those arms has a length of exactly 2.
I see.
If you find that specific structure anywhere in your graph, it breaks the caterpillar definition because the vertices at the ends of those 3 long arms can't all lie on or be adjacent to a single unifying spine path. It's the minimal possible departure from that path-like structure.
Finally, we had to consider the directed version of trees, which are essential for modeling hierarchy and flow, branchings and arborescences.
Right, a branching is just a directed tree. When the flow radiates outward from a source, we call it an out tree or an arborescence rooted at some vertex R, and it has 2 strict rules. The root R has to have an in-degree of 0, nothing flows into the source, and every other vertex must have an in-degree of exactly 1. Only one edge is allowed to flow into it. This perfectly captures a dependency structure, like a command chain or a hierarchy of prerequisites for a project.
And the reverse orientation would be an in-tree.
An in-tree where the flow moves inward toward a sink. Here, the sink has an out degree of 0, and every other vertex has an out degree of 1. These are crucial for modeling things like data flow and network synchronization. The source notes mention Edmonds' theorem, which is a powerful generalization that extends the matrix tree theorem to count disjoint branchings in general directed graphs.
We have completed our deep dive. We've gone from the basic definition of acyclicity all the way through to these advanced enumeration methods. This should provide you with a really comprehensive and robust set of notes on tree structure. Before we wrap up, let's just consolidate the most important takeaways.
We covered those foundational equivalences that make a tree the most efficient possible structure. Let's quickly run through them again, using that mnemonic style to help them stick.
Great idea. First, trees are born where cycles die.
They are acyclic and connected,
They must have n-1 edges.
the exact minimum required for connectivity.
Every edge is a cut edge.
Cutting any single link severs the structure.
Add one more, a ring shines through.
Adding a single link guarantees exactly one cycle.
The center is simple.
It's either a single vertex or a single edge.
And we count with Cayley's formula.
The number of labeled trees is n to the power of n-2, all thanks to the proof arcade.
The synthesis here seems clear. The mathematical properties of a tree, the unique paths, minimal edges, guaranteed connectivity, they make it the blueprint for optimal non-redundant connection.
Absolutely. And understanding these constraints is essential for designing efficient networks that avoid unnecessary costly loops.
And those open questions we touched on show that even these simplest structures harbor these deep, unsolved mysteries about their symmetries.
For sure. We ended with the decomposition conjecture. Can the complete graph K2n+1 always be perfectly tiled by 2n+1 copies of any tree T with n edges? We know it's true if the tree is graceful, which brings us back to Rose's conjecture, but that universal gracefulness remains unproven.
If every tree is indeed graceful, the implications for graph symmetry would be just staggering.
They would. It would imply this massive, inherent, beautiful symmetry in how graphs can be built and broken down. And that brings us to our final provocative thought for you to carry forward based on everything we've reviewed.
Let's hear it.
If Rose's conjecture is true, guaranteeing that every single tree is graceful, what practical implications does
You
this
can do
profound
it.
universal
Let's
ability
work
to
today
perfectly
to make
tile
tomorrow
complete
a better
networks have for
day.
establishing robust
Okay.
redundancy and
You can
maximum
do
load
it.
efficiency
Let's
and high
work
density
today to make
real-world
tomorrow
data
a better day. Okay. You can do it. Let's work.